So right now we have, let me go ahead and slide this circuit into the picture here. I've got 3 light bulbs here that are connected in series with each other. And each of these light bulbs requires 3.5 volts to reach its proper intensity. So as we come up in voltage, let me turn out the current limit. As I come up in voltage, I'm starting to see some light. There I'm at 5, 6. Okay. I'm going to need about 10 volts to get full intensity. Okay. This is a series circuit. So what we're talking about, I've got 3 bulbs instead of just 2 bulbs, but if you can see this, I've got the signal generator. I got 2 bulbs on the diagram here. Got 3 bulbs in reality. But if you break the circuit at any point, all of the lights go out. And it doesn't matter which one will out. Stick this back in the circuit here. Okay. Doesn't matter which one I pull out. The circuit dies because we have broken the whole circuit. Get back in the right set of contacts. And if you notice the intensity of the light there, it's taking 10 volts to do that. This light over here indicates the current in amps. So I'm running almost half an amp, 0.48 amps in this circuit. Okay. Now, let me turn this voltage down. Now I'm going to connect the lights in parallel. Okay, they're in parallel. Connect up the ground. And as I come up, okay. Here I am, 3.6 volts. Look how bright they are. Look at my current. I'm pulling almost 1.5 amps now. Before it was half an amp. We're talking about lights wired in parallel, like the bottom part of this drawing. Got your power supply, 2 lights. So I need less voltage because each light is connected to the voltage source directly. Up here in series, the current had to go through each light. The first light's connected directly to the voltage source, but the second one is only connected to the first light. And in our case, the third one was connected to the second light. So all of the current had to go through the same point, which is why when you would pull any bulb out, the circuit would die. Here, each one is connected directly to the voltage source, so each bulb sees the full voltage coming out of power supply. But these bulbs require 1/2 amp of current at their proper voltage to have their full intensity. So this one, because they was all running one behind the other and the current is the same in a series circuit, the 1/2 amp on the first bulb was also the same 1/2 amp on the second bulb and on the third bulb. But here, in a parallel circuit, the voltage and the current can flow through this bulb or can go through that bulb. So this bulb can flow 1/2 amp and this bulb can flow 1/2 amp. And if I had a third bulb, it would flow 1/2 amp. That's why we're seeing much higher current. But an interesting thing about this circuit, I take one bulb out, the others keep working. That's because if I pull one bulb out, the current can still flow through the other bulbs. So that's your parallel circuit. The first one was the series. And that's true whether you're dealing light bulbs, switches, resistors, whatever you're using for your circuit. When it's in parallel, there's alternate paths for the current to flow. And when you put the parts in series, whatever flows through the first one has to flow through the next one and keep going for as many components as you have. All right. Any questions on parallel versus series? Let me go ahead and get this disconnected. So that's DC. All right, now we talked about Ohm's law last week. If we knew the value of 2 of the 3 components, then we could figure out what the value was on the third one, current, resistance, voltage. So I'm indicating 2 of these here, current and voltage, and I have a resistor in my hand. Now I'm going to turn this voltage down to a volt. All right. Here's a resistor, talking DC. When I make the connection, I get 0.6 amps. So what is my resistance? Anyone want to tell me? This resistor is a 1.5 ohm resistor, 10% tolerant. So it technically should have been reading 0.66 amps if it was exactly on, but like I said, it's a 10% tolerance and 0.6 is within the 10%. And if we increase the voltage, you can see the current goes up with it. Now I'm going to stop there because this is a 2-watt resistor and almost 1.5 volts, almost an amp. That's 1.5 watts, right? Volts times amps is your wattage. So if I go much higher, I'm going to start pushing the limit on this resistor.
Smoke test.
Okay, here's another resistor. It's the same physical size. But if you notice at that same 1.5 volts, there's very little current. In order to get 1/10 of an amp, I'm almost 3.5 volts. If I'd gone to 3.5 on that first resistor, I would have exceeded its wattage. It might have started smoking on me. But on this one, I'm running 1/3 of a watt. At double the power, at double the voltage, I'm running much less power in this resistor. So 3.5 volts, 0.1 amps. What's the resistance on this resistor? I can tell you the color code tells me it's a 33 ohm resistor. It's orange, orange, black. Orange is 3. And the black tells me that there's 0 multiplier. In other words, you don't put any zeros behind the first 2 digits. So this would be a 33 ohm resistor, and that corresponds. Got one more resistor here. I'm running 1/10 of what I had before for current. Same voltage. Even if I crank this voltage way up, I'm not getting much current through it. I'm at 15.5 volts, don't even have 1/10 of an amp. And I can tell you from the color code, this one is red, red, brown. The red is 2. So I got 2, 2, and the brown tells me that there is 1, 0. So it would be 220, 220 ohms. So Ohm's law does actually work. Something I want you to be aware of. I got 1.5 ohms, a 33, and a 220 ohm, and they're all physically the same size. The size of the resistor is an indicator of how much power it can handle, but not what its resistance is. That's why we have a color code to tell us what the resistance is. We can also verify that resistance. Is this readable? That 220 ohm resistor says 220.1 ohms on the multimeter. So we can use the color code. We can check it with the multimeter, or we can run a current through it with known voltage and calculate the resistance that way. All right, and get rid of these resistors. Any questions on that? Okay, next thing I'm going to show you guys. Well, I'm going to move this tripod. Try not to make everyone seasick here. If that. Okay, I got rid of one of the backlights. What you're looking at here, the lower unit is a signal generator. The upper unit is what we call an oscilloscope. And an oscilloscope allows us to visually observe signals, AC signals that are varying in their voltage and frequency. Now, the way this works, there's an electron gun at the back of this unit, sends out an electron beam. When the beam hits the front face here, it glows. And we can control how fast the beam moves across the screen. We can speed it up a lot. We can slow it down to a crawl. Okay. Up and down on the screen is voltage. So right now I have the input grounded, and all you're seeing is just a blank trace. It's not going up or down. It's not indicating any change in voltage. If I put a signal in, make a better connection here. And I'm going to change the amplitude on this thing to 100 millivolts. Okay, I lost my trace. All right, as you can see now, it's indicating above and below. Let me go back to ground. Right here in the center of the screen, this center line, that's ground, that's 0. The signal is going above and below that line. But you really can't tell much other than the fact it's going above and below the line, but you can't really see the signal. If we accelerate the trace, oh, wrong knob. Where's the hold off button? Okay. Now you can see the voltage is going up and down, and you can actually observe that signal. Any questions about this so far? So this thing is showing us up and down is the voltage, left to right is time. Signal start, or the beam starts over here, moves across. And it moves across at a speed that we can select so that the faster the signal is, we can speed up the beam so that we can observe that signal. If you're going too slow, you can't tell much about it. All right. Now, this signal generator can do a couple of interesting things. For one thing, I can change the frequency. I got frequency selected, and I can go to, let's go to 3000 hertz. The distance between the peaks is time. Less time between the peaks means it's happening faster. So this is a higher frequency, which 3000 would be higher than 1000. We can go to 10 hertz. And if we slow that down, it's the same thing we were seeing before, just a whole lot slower. So as these get closer or further apart, that's an indication of frequency. We can directly actually read that to determine the frequency. But understand, the closer they are, the higher the frequency. The more spaced out they are, the lower the frequency. All right, so one of the things I can do, I can set a starting frequency here. I'm going to set 500 in it, 500 hertz. And then I'm going to come up with a stop frequency, and we'll set that at 10 kilohertz. And then I can tell it to sweep. We're going to accelerate this. And one other thing I can do is tell it the time I want it to do that over. Let's do it over 5 seconds. So what you're seeing here is the signal is going up and down in frequency. But if you notice, the height does not change. You're getting the same voltage indication, whether we're talking the high end of the frequency or the low end of the frequency, that it's sweeping back and forth across. So if the voltage changes, that's an indication of either a larger amount of signal getting through, or if it goes down, then it's showing you that there's less signal getting through. All right. So let's talk about our friend, the capacitor. I got to get connected correctly here. All right, I got a capacitor in the circuit. And I'm going to make a slight change here. I'm going to change the minimum frequency to 100 hertz. All right, so there's maximum frequency. There's minimum frequency. But if you notice, as it goes towards the minimum frequency, the voltage appears to be a little less. If I set the start frequency at 10 hertz, you're going to notice that voltage gets very weak. Let me increase this time. Let's go to 10 seconds. Here at the high frequency, we're the same voltage through the capacitor that we was without the capacitor in the circuit. But as we go down in frequency, that signal gets lower. The strength of the signal. I'm going to just directly input different frequencies rather than sweeping it. It's a little more obvious if I do that. Okay, there's 10 hertz. As you can see, it's going down about a square and a half. I go to 20 hertz. If I go to 100 hertz, it gets larger. If I go to a kilohertz, 1000 hertz, it gets larger yet. So this is what we was talking about last week, capacitive reactance. The AC resistance of a capacitor is higher at low frequencies, and that resistance goes down as the frequency goes up. All right. Now we're going to look at an inductor. With an inductor, let me do it this way. Now I'll go back to this one here. As I go up in frequency, there's 9,000, 12,000. 20. It's 30. The signal is getting a little smaller. So as we go up in frequency on an inductor, the resistance goes up. The coil of that inductor is resisting the change in voltage. And the more that voltage is trying to change, the faster it's trying to change, the more the coil is resisting it. So we end up with higher resistance at higher frequencies. Now, if you put the two together so that you have the inductor and the capacitor in circuit together, and I'm going to go back here to 10 kilohertz. All right, what am I not getting here? I've got this connected, I got that connected. I'm not getting a good clear signal here. Got a good signal there. Make it a little bit brighter. We'll try this again here. A pretty steady current. It's supposed to be a frequency filter here. And I think one of my components just went bad on me. Where am I at? 18. Yeah, I think one of my components just went bad on me. When you have the capacitor and the inductor hooked in the circuit together, this way here, we have the capacitor and the inductor. Here's the signal generator. Here's the scope. At frequencies below the resonant frequency of this filter, as you go down in frequency, remember the resistance gets higher in the capacitor. And as you go up in frequency, the resistance increases on the inductor. But when they are both equal, they cancel each other out. There is a frequency where this resistance and this resistance, or reactance, when you're talking AC, you should say reactance, then they cancel each other out and you get maximum signal through here. And then when you have the two connected in parallel, see here we're series, here we're parallel. When they are connected in parallel with each other, you get the same effect, except that at anything higher, this one conducts, and anything lower, this one conducts, but there is a point where they tend to cancel each other out and you get minimum signal going to the scope. So this acts as a pass filter. This acts as a notch filter. It will decrease the signal at a given frequency. This one maximizes the signal at that resonant frequency. Okay, I don't need the signal generator. Okay, let me slide this over just a little bit. Now, what I have here is a transformer, a small transformer. Takes 120 volts in, steps it down to 6.3 volts of AC. And if we connect across the transformer, then all right, there's our AC signal. This is what is in your house current, in your wall sockets. AC signal, 60 hertz, 60 cycle. Now, connected to this transformer, I have a diode. So here, I can get a connection. Come on, give me the. The funny feeling, this is what went bad was this set of test leads. There's our AC. This should be rectified DC here. All right. I'm going to take, what time we got? Let me take a 5-minute break here. I'm going to swap oscilloscope. Something is wrong here, and not exactly sure. This is a scope that I acquired last year at Dayton. and I haven't used it much until tonight. So I'm going to swap scopes. Okay. Now let's see if we can get the AC signal. All right. Yeah, something in that other scope. I'm not sure what, but I'll look at it. All right. So here's our AC signal. If we go through the diode, the bottom half of the AC disappears. If we go through the diode the other way, the top of it disappears. Now we see the bottom of the AC signal. Diode only lets it pass in one direction. So if you reverse the diode, it's going to pass in the opposite direction. If you take 4 diodes and you connect them correctly, you get a full wave rectifier. And what that does, let me go the other direction here. I'm going through them reversed. There we go. We're not looking at AC. There's no signal. Everything is above the zero line. This is AC. There's through the diode. The negative is gone, but the positive is there. It's above the zero line. But if we use the full wave rectifier, we're taking what would be the negative pulse and we're inverting it so that we get the positive pulse and the negative pulse. We're getting both of them. And that gives us what they call full wave rectification. We're getting both halves of the AC circuit and turning both halves of that AC into pulsating DC. So we end up with a more efficient way of converting AC into DC. That allows us to build power supplies that are more efficient. Also allows us to get more power out of it.
You said that was 4 diodes in order
Yes.
to make it do that?
Yes, 4 diodes connected in what's known as a full wave I mean, yeah, full wave rectifier circuit. You have to connect them in a certain way, but when you do, then you are providing a path for the electrons on the positive side and on the negative side to get rectified. It's a fairly simple circuit, but you have to do it right. Years ago, almost 40 years ago, I built a rectifier unit that for a machine shop, and I screwed up. I got two of the diodes in backwards, and when I connected it across the 230-volt circuit, instead of being a rectifier, it was actually a short, and the diodes literally exploded. There was an arc that lasted for, just like a lightning flash, but it embedded particles of those diodes in my forehead because I didn't have the door closed when I made the connection. A lot of lessons learned on that one, I can tell you. So yes, you have to connect them correctly, but it will work. And in fact, let's see if I can get this up here where you can see it a little better. This one component over here, there you can see it a little bit better. This one component over here, that's the diode. So I have it tied into one side of the transformer here. And then I was connecting on the other side before. So that's the AC, that's through the diode. And then this component here, that is a full wave rectifier that comes as a package deal. You get one component, it's got the 4 diodes in it, it's rated for a certain voltage and a certain current. You put AC in on these 2 legs, and you get DC out on these 2. Or you get pulsating DC. Need to be a little more specific. It's pulsating DC. Okay, so I'm going to take a capacitor. This is an electrolytic capacitor. It's 1,000 microfarads at 35 volts. And I'm going to connect it. Make sure I do this the right way here. This is the short one, it's the negative. Come on. You see what happened? I turned that pulsating DC into a much smoother DC. When you have a signal like this, you can smooth it out. It's called a filter capacitor. It's not a type of capacitor, it's what you're using it to do. And I'm using this capacitor across, get it connected right here. I'm connecting it across the signal, and I'm turning that pulsating DC into pretty smooth DC. If I was to use a larger capacitor, not, more capacitance, more microfarads, or actually, then it would be even smoother yet. I'm looking for a small capacitor here.
What is the benefit of making that smoother? Like, what does that actually do to the radio or whatever?
Well, AC signals and pulsating DC can inductively couple. In other words, if you have two wires next to each other, one of them has the pulsating DC signal on it, the other one is, say it's an audio signal coming from a microphone. If they're close to each other, this varying magnetic field that is created around the wire, because this is varying in voltage, the magnetic field that's created by this will also be varying. And it can, if they're close to each other, it can inductively couple, just like a transformer can take the 120 volts that's coming in and it inductively couples it to the output. I've got 6.3 volts over here. So the transformer is basically a 20-to-1 transformer. I can get more current out of here, but less voltage. But there's no direct connection between the windings on this side of the transformer back here and the windings on this side of the transformer. It's two isolated coils. They're not touching each other, they're not connected to each other directly, but they are wound around each other so that the magnetic field in the one affects or creates a magnetic field in the second one. So if you have this pulsating or AC signal, it can do the exact same thing. If you've got two wires running close to each other, you can get what they call noise. It's the undesired signal from one place to another. It's transferring from this line here over to, it could be the input to your audio amp, it can be signal coming from a microphone, but some low level weak signal that you're going to amplify to make it useful. But if the two wires are close to each other, then you can get the inductive coupling from one to the other, and you're going to pick up that noise. And when you amplify it, you're going to get undesirable. You've heard hum in a radio where it just sits there and just it's the 60 hertz hum in your wall outlet. That's because somewhere in that radio there is coupling occurring between the AC coming into the radio in the form of power from your wall and the radio signal that you're amplifying that you're trying to listen to. So if you can filter it, get it smooth, then it reduces the amount of what we call noise that occurs in the circuit. Does that explain it?
Yeah, I got it. Thank you.
Okay. Yeah, I'm going to move this out of the way. Now let's see which is the negative side here. This out. Okay, this is a solar cell, a small solar cell. If I get out of the light, it's producing a signal. Give it some shade, that signal goes down. It's generating voltage just from the light. And we can use the solar cell get this a little closer. This is a very large capacitor. It's 1 farad, not a microfarad, 1 farad. I've got a very small diode here. And the idea is we produce the voltage, but even when I cover it up, this capacitor acts like a small battery. I cover up the light source, but the capacitor, which has been charged up by the solar cell, it maintains the voltage. I'm not getting any change at all in the output. If I go back to the other side of the diode, so again, the diode acts like a one-way check valve. It lets the current flow into the capacitor, but when I block off the light source where it's not able to produce voltage anymore, it doesn't drain back. It holds the voltage in the capacitor. So this is a handy little circuit. You could use, charge up this capacitor, and then even when nighttime comes, the capacitor can power whatever circuit you're trying to run until it discharges. And then when the sun comes back out again and shines on the solar cell, it'll charge it back up. That's how those little patio lights and pathway lights you see that are not wired into anything, you just set them out in the ground, stand them up along the side of the sidewalk. That's how they work. They got a solar cell. If you look at the top of them, you can see the solar cell. It charges up. Usually it's a rechargeable battery, but a large capacitor would do it too. When it gets dark, they light up and they'll run, if not all night, at least most of the night till the sun comes back up again. All right, let me see if we can go back and do the signal generator on that filter and see if we can get it to work. Okay, I think something on that scope actually went bad, but like I said, I'll have to check into it. Something wasn't working like it should. Uh, uh, Okay, there is the AC signal coming out of our signal generator. All right, 0 is in the middle of the squares, up, down. I'm shorting out the leads. That is straight inductive coupling coming from the wiring in here, the lights. As you can see, that's noise. Undesirable signal. All right. So we're going to go back again. And I'll leave these two connected and use these two. All right. So I'm running 5 kilohertz. Still not showing the effect of resonance here. No, still think I got a bad component in here. As you can see, as I'm going up and down in frequency, signal strength is not changing. And right around 7,000 hertz, there should be a definite change. And I'm not getting that. I don't know. It worked fine yesterday. Doesn't that figure? Um, there was a very definite point right in here where signal drastically decreased and then it went back up. I'm not sure what happened. Okay, I'm going to move the camera back over here. Last year, somebody asked me, they said, oh, this is all fair and good, but how can we use it? They wanted to know how they could put this knowledge for practical use. So let me tell you a problem I had last year. I put a radio in my car. Nice little new mobile radio. Got it wired in. All right, where's my pin? I had a pin here earlier. There it is. Okay. So we're going to start with, here's the way it was wired in to start with. Schematic symbol for a battery. And I ran wires from inside the vehicle all the way through the engine compartment to the battery. And then the radio. There's the plus side of the battery. Here's the minus side of the battery. And I'm going to connect into the radio. And this worked fine with one little problem. Anytime that I would start the car with the radio on, the radio would blank out. It would reboot. And it takes it 3 or 4 seconds to come back up and be back in radio mode. It's like every other modern radio. It's got a computer on the inside and it has to boot back up, just like your phone does if you shut it off, or your computer or whatever. Well, that's kind of annoying if you're talking to somebody on the radio when you're stopped and then you go to start the car and you can't hear them for 4 seconds when they're talking to you. So how can we fix this? Any suggestions?
Capacitor?
Okay. Where would we put the capacitor?
I would imagine on the positive line.
All right, so I got a capacitor on the positive line. Where's the other side of it going to go?
On the other side of the positive, like in series or whatever you call it.
Well, now, if I put a capacitor in series, if we do this, then there won't be any DC flowing through the capacitor.
Uh,
Here, let's take a capacitor. Here's the negative side of the capacitor. Let me double check what this thing is rated for voltage. Okay, 35 volts. So I'm fine. Turn it down a little bit. Okay, so I connect the capacitor in series. How much current do I have flowing?
well, you would have 12 volts from the battery, correct?
Well, I got 14 volts here. Let me see if I can get this a little better in the picture. I got 14 volts, and I've got no current flow through the battery. If I connect them up, I get current flow. But if I go through the capacitor, there's no current.
Okay, I'm confused.
Well, that's why we're doing this. You cannot feed DC through a capacitor. Remember,
okay.
the lower the frequency, when you're dealing with AC, the lower the frequency, the higher the resistance. When the frequency becomes 0 hertz, in other words, DC voltage, there's no current because the resistance is so high. What you have when you have a capacitor is 2 conductors separated by an insulator. That's the definition of a capacitor. 2 conductors separated by an insulator. That insulator can be air, it can be mica, It can be a number of different chemicals, but they're insulators. So you do not get DC flowing through a capacitor. If you connect this capacitor up, we've done it here. We've applied, well, let's go ahead and make it up to 15 volts. All right, we've applied 15 volts into this capacitor. When we first connected it, if it was discharged, electrons flowed in, you built a charge up, there's electrons on one side of this capacitor, the other side is grounded, we build up a charge. It stores the electrical charge. Bring a voltmeter in here. I'm going to disconnect the power. I'm in DC volts. Get this over here a little more. I got voltage. That capacitor is charged, but as you can see, it's decreasing in voltage. It's like a battery running down, only it's a very small battery. How small is it? Here's that 220 ohm resistor. Let me see if I can get this. That fast, we drop the voltage to 0. We completely discharge that capacitor in that short amount of time. And if you watch the amp meter, it went up for just a split second. That was that initial current flowing in and charging that capacitor. And once that capacitor is charged, there's no more current flow. Is it charged? Come on, stay out here. Yep, we got to charge it back up. So a capacitor will hold the charge, but we can't run any current through. So knowing that, how would you connect the capacitor in the circuit?
I guess in parallel then, right?
In parallel with what?
With the hot. I don't know.
You're right, we're going to do it in parallel, but we're going to do it parallel with the radio. So you're going to build up a charge here. It's like a small battery, remember. If this goes away, there will be some charge here to keep the radio running. But this circuit has a slight problem. This doesn't go away. What happens on this end when you hit the starter on the car, the voltage in this line right here drops way down because the starter is pulling so much current, it pulls down the voltage and it'll drop down 6 or 7 volts sometimes if the car's working in the wintertime trying to get started. So what we have here, we've got a charge, but as soon as this side goes down to 6 volts, what's going to happen to our charge? Somebody?
You're going to lose your charge at that point.
Yeah, our charge is going to flow back in the wire towards this, trying to feed that low voltage. It's still going to drop, and our radio is going to recycle.
So
How
can you
can we
add an
stop
inductor
that?
in there with the circuit?
Say again?
Can you add an inductor in there as well to as a means of generating power?
Well, we
Or
can.
does it end up with the same thing? It's going to lose the
What we
electrical.
don't want is we don't want this charge in the capacitor to flow back when the battery has that low voltage for that moment when you're starting. How do we stop it from flowing back?
Put a diode
Diode.
in there.
Yeah, we put a diode in it. So what we're going to do, I'm going to put a diode in this circuit. Now, when the voltage at the battery drops down to whatever, this charge here can't flow backwards in the battery. So backwards into the main battery. So this will hold a charge, hopefully enough charge to keep the radio operating while the car is starting. All right. Now we're doing pretty good here, but there's one additional problem with using a big capacitor in the circuit. Capacitors can charge very quickly. You remember this? Let me discharge this capacitor again. Okay. Watch the current. Can you guys see it? Yeah. Watch the current on the power supply. It jumped up for just a second. In fact, it got so high that if you notice the green light that came on, that green light is a current limit. It's telling me that the limit I had selected in the power supply was being exceeded. Let's see if we can find a real peak here. And it's charged that fast. So it will exceed what you have. This here tells me what I have my current limit set at. I got it set for almost 2.5 amps. And it exceeded that fast. So that creates a little problem. Because diodes are current limited. If you exceed the current flow through the diode, you can burn up that small little PN junction that makes it a diode. So what else can we do? What can we do to reduce the surge of current?
Add a resistor.
Well, if we put a resistor in here, what happens to the voltage out here?
Yeah, that's going to drop as well.
Right. So what do we have that we can use that will resist a current change, but not act as a big resistor to keep the current from flowing? Somebody said it earlier. We can put an inductor in the circuit. If we put the inductor here, when we start out, this capacitor is completely discharged. we plug it in. You're going to get this inrush current that's trying to charge this capacitor. We don't want to burn up this diode. So this inductor, when you get that inrush of current, that creates a magnetic field that slows down the current. And so, yes, it charges. It charges pretty quick, but it does reduce the inrush current. So we've now have protection for the diode. The diode keeps the current from flowing backwards. And then the capacitor holds the charge so that while the car is starting and the voltage is low over here, the radio still has enough voltage, it doesn't have to reboot. Can you see that? This here is the input. Hot side, ground side. No, I got it backwards. This is the input. Comes from the battery. Red is hot. In this case, white is ground. I didn't have any black wire the right size. Here's our inductor, a wound up coil. Here's our diode. So through the coil, through the diode, there's a couple of capacitors. You notice the capacitors are connected across the circuit, just like the diagram shows. The inductor and the diode are connected in series, just like the diagram shows. And this almost works. My problem is I don't have enough capacitance. If the car starts quick, I'm okay. But if it is cold and it lags just a little bit getting started, then the radio reboots. So what I need to do is add some more capacitors or bigger capacitors. These are 1,000 microfarads each. That they're the same as this one here. This is 1,000. Where is it? Yeah, here we go. 1,000 microfarads at 35 volts. That's what these are. So I'm going to get some more capacitors. I came up with a circuit last year. I ordered the components, just never got it built until recently. And then, like I said, I have a problem when it's cold. It still reboots the radio. So I'm going to add some more capacitors, and I'll see if that fixes it. But you can design your own solutions to electrical problems with a little knowledge. Everyone understand that? Any questions? Can you hear me?
Yeah, if there wasn't like a huge draw on those capacitors, like if you're just using it for a little LED or something, how long will those capacitors hold that charge?
Okay. Um, give me just a minute here.
Okay.
All right, we got to do a little bit of math on this one. I'm going to get my soldering iron out. Solder. Okay. Here's a little diode. Turn the voltage way down. Come on. All right, so I got a light emitting diode here. If I'm connected the right way, as I come up in voltage, I'll reach a point where it starts conducting. Ah, there we go. So at 2 volts, it starts conducting. You know, we talked about forward voltage drop. Well, that's it right there. It takes 2 volts, about 1.8 volts, to get the conduction. Can you see the LED is trying to light up? And if I go up, so at about 2.5 volts, I've got good brightness on the LED. And I'm pulling about 40 milliamps. Now, if we wanted to know what it was really pulling accurately, this is only indicating hundredths of an amp. We could connect now we have an amp meter. I put it in the amp position. And let's see. This way. I'm over here to milliamps. Okay, I'm running 37 milliamps, 38. And I've got a fairly bright bulb. We could come up maybe just a little bit more. There's 40 milliamps. Okay, so we know what current we want. We want 0.04 amps. And we're charging this capacitor up to 15 volts. If I put 15 volts across this LED, I'd blow it out. So we can't just connect the LED to the capacitor directly. So we know what we want for current. We know what voltage we're going to be applying to the to the circuit. We're going to be going 15 volts. So what resistance do I need? Remember Ohm's law? E equals I times R. Or you can take the 15 volts, divide it by the current, and it'll tell you what the resistance needs to be.
So would that be 5?
Pardon?
5, is that right? So you divide it by 3?
Well, you take the 15 volts and you divide it by 0.04.
Oh, 0.4. Okay. Yeah. So that number would be it.
Yeah. What do you get? Somebody got a phone handy? Calculator on their phone?
I got 375.
Okay.
I'm not sure why that doesn't seem correct to me.
I got 375 too.
All right. I'm gonna look real close here, see if I can find. I thought I had. That's 1,000.
While you're looking, can you connect like resistors in series or something to like make the exact number you need, or do you have to use like one resistor?
You can connect resistors in series or parallel.
Uh-huh.
If you connect them in series, you can add up the resistances.
Okay.
So if the first one is a 100 ohm resistor and the next one is a 50 ohm resistor, you're going to have 150 ohms.
Gotcha.
Okay. We're going to try this. It's not the 375, but it is. Let's go back to resistance mode here on the meter. No, it's a 240. So we'll charge this thing to 10 volts instead of the 15 volts. And if we only use 10 volts across the capacitor, then that should give us 40 milliamps. I'm going to do some quick down and dirty soldering here. Gotta wait on the soldering iron to heat up. Should have turned it on when we were doing the other. Of course, my good fixture is inside the shop here, or I went and got it. I will be able to. Come on. There's our circuit. We have. Turn this on. Here's the positive side of the capacitor over here. You can see the negative side has mark on it. We come through the resistor, through the diode, back to the capacitor. We've got a circuit. And we're going to turn the voltage up to 10 volts. Want to charge it up? It's charged. See it? See it bleed off? When I say it's a small battery, I mean it's a small battery. But that's 40 milliamps. Charge it up, let it discharge. Does that answer your question? How long it'll do it?
Yes. Thanks.
Was that the answer you expected?
No, I thought it would last a lot longer, actually.
Well, it's only 1,000 millifarads.
So
In
I
other
imagine
words-
there's some calculations you could do with the amount of farads as far as
Yes.
how long that would
Yes,
last.
Here it is.
Okay.
And it's a little more complicated formula than we're going to get into tonight. But yes, you can do it. You can find that formula online
Okay.
and it will tell you how long you could pull a certain amount of. As you start pulling, if you noticed it went dim over time. It didn't just go out,
Right.
but it didn't stay bright for a while and then start dimming. Like if it was a battery and I had that battery connected across that,
Uh-huh.
then it would take hours, but eventually the brightness on that LED would start to decrease as the battery reached the end of its life and started losing voltage. So it would stay bright for a long, or it would maintain its proper intensity for a long time at 40 milliamps because the voltage curve on the battery is relatively flat. The voltage curve on a discharging capacitor is a curve.
Gotcha.
So what happens is you start off, you're at that maximum voltage. As soon as you pull anything out of it, that voltage starts decreasing. You remember the first time that I put the voltmeter across the charged capacitor and we could watch the voltage bleed down slowly?
Mm-hmm.
Well, the reason for it was being so slow, that voltmeter is the equivalent of a 10 million ohm resistor. So yes, it's a very slow discharge when you're using the voltmeter across that capacitor.
Gotcha.
We had 350 ohms across that this time. So yeah, it discharged a lot faster. But the problem is that as soon as you start pulling current out of that capacitor, the voltage starts decreasing. And the lower the voltage gets, then the less current that same circuit is going to pull. Because as the voltage goes down, the current goes down if the resistance stays the same. So you end up, that's part of why that formula gets a little bit complicated, is because the voltage is constantly changing as it's discharging. I may steal 10 minutes of somebody else's class time. And if I can figure out what went wrong with my resonant circuit, I may do that demo in the future just so you guys can see it. But I don't know why that didn't work. It worked fine yesterday. I don't know. I had the signal generator apart. Some of the push buttons on it were not working properly, so I took generator apart and fixed the switches. There's actually a little flat metal spring that's supposed to be in each switch, and a few of those flat metal springs fell out, and they was just laying inside. So I put it back together, got it right, and it was, like I said, it was working fine yesterday. So I don't know, but
What?
if it comes to it, I'll try and
get that demo working properly and do it for, like I said, still 10, 15 minutes of somebody's class time and do that.
Let me add one more thing.
Okay.
When you were talking about DC voltage,
Mm-hmm.
most devices like radios work on DC voltage, and AC is what's supplied to your house, and the power supply he was showing you is how they generate DC from AC and then filter it. If it's not filtered, you get that hum he was talking about in your device. But he didn't actually mention that all amplification devices run on DC, even if they're vacuum tubes.
Yeah, they use DC for the power source, but they are typically amplifying AC signals. That's what's interesting about it.
Exactly.
And in a lot of radios, well, basically all of them that run off of house voltage that you plug into the wall will have a power supply built into the radio or as a separate box that takes that 120-volt wall socket, converts that to a DC voltage, depending on the radio. If it is a mobile radio, like you would mount in your car or whatnot, you want a power supply that's going to put out roughly 13.8 volts, because that's what your car runs at when it's charged and the alternator's putting out power. So you want a regulator that's going, or a power supply that's going to maintain a constant voltage DC with enough amps to run the radio. And if you have a tube radio that has, the older technology and output tubes in it, then, or even amplifying tubes in it, then they run off a lot higher voltage. So they may have a circuit in there where you take the 120 volts from the wall outlet, run it through a transformer, and that transformer produces, it's got multiple windings on it so that it's producing multiple voltages. Some of those can be well over 1,000 or a couple thousand volts. And some of those windings in there may produce 6.3 volts to power the filament on the tube. So you're going to get multiple voltages coming out of this transformer. You're going to want to filter them. You're going to want to rectify them. So you're going to have multiple diode circuits. You're going to have capacitors, like I showed you the smoothing. You're going to have multiple of those, and there'll be a lot larger capacitor because you're pulling more current in order to get that filtering. When you're pulling the bigger load, then you need to have a larger capacitor to maintain that charge between those pulses. I wasn't pulling anything out of that capacitor. I was just connecting it across the diode. So it was charging up to its peak and staying there because there was nothing pulling power out of that capacitor. Nothing trying to discharge it. So it just sat there pretty smooth at peak. If you was pulling power out of that capacitor, it would smooth those pulses somewhat, but the more current you was pulling out of that capacitor, the more you would see the pulses. So the larger the capacitor, the more smoothing you get. And we're talking about the actual microfarads or farads, the actual capacitance of that capacitor. When I say a larger capacitor, I mean more ability to hold a charge. So that's part of those power supplies. It's an important part of those power supplies is the filter capacitors. And then you'll have a circuit that regulates and maintains a constant voltage coming out of that so that it can feed whatever it is you're going to power, whether you're talking powering a tube, powering a mobile radio that runs off of the 13.8 volts, or whatever you're running. Because again, having a smooth source of DC is important to avoid noise transfer inside your circuit, because your circuits are dealing with small, and when I say small, some of them are microvolt signals. So we're talking very small signals. It wouldn't take much noise, interference, inductance from another circuit to swamp the circuit, the signal you're wanting to work with. So smoothing is an important part in circuit design for power supplies. But yeah, you can use a transformer to get almost any voltage you want out of the transformer, multiple voltages if you have multiple windings, and they can get pretty complicated. Any other questions? Anybody going to be designing circuits this weekend? No?
No, I don't think I'll be trying that, but something I was thinking about a moment ago, back during Christmas, somebody brought up to me that if you took a slow motion video of some Christmas lights that were LEDs, they will show up as flickering in the slow motion. And I suppose it would be, considering their diodes and it's on AC current, that you're essentially seeing that pulsating electricity through the flash. Would I be correct in that? Because it's not able to go backwards.
You're probably correct on that, but it depends on if they're just running them straight on AC, then yes, that's why they're flickering. But a lot of times what you're seeing is they're actually running a power supply and they are converting the 60 hertz AC into DC. And then they're feeding that DC through another circuit that turns on for a very short period of time, then turns back off, turns back on. And it's actually running that LED at a higher current than what you can maintain through the LED without burning it up. But because it's pulsing, you can run a higher current for a very short period of time, and then you turn it back off again. The net effect is the LED appears to be brighter even though it's off part of the time. But your eye sees it as being a brighter LED. And so the LED headlights, a lot of times they're set up exactly that way. They're not a constant light. If you put a device in front of them that can strobe that light, you will see it's actually flickering on and off at a constant rate. But it's designed to do that because it appears brighter when you do that. It's just one of the characteristics of our eyes, is that even though that bright pulse isn't there the whole time, we see it as brighter. So that's the human eye. And I don't know if other animal eyes do it too. I assume that they all work about the same, but yes, human eye responds that way. A human eye also has persistence. So that's why you can go to the movie. It's a flickering image. But if you go to the movies, it looks much more constant because it's flickering fast enough. Our eyes see it as continuous motion instead of one picture and another picture and another picture, each one slightly different. So probably if it's running on AC, that's the flicker you're seeing if you run a high-speed camera. But it's also possible that they're making the lights appear brighter by running them through that circuit.
Okay, interesting.
Yeah, 5 years ago, I didn't know that about LEDs. But yeah, I've a lot of these flashlights, LED flashlights, are the same way. If you take a light sensor, electronic light sensor, and you run it through an oscilloscope, you can see the pulses. So, yeah, it's there. Any other questions?
I'll make one comment, Rick. This is Harry.
Yeah.
Going back to where Chris asked the question about why you wanted to smooth the alternating direct current.
Yes.
As
Pulsating
you were,
direct.
yeah. As you were explaining that inductive coupling, it's the moving magnetic field across the other wires generating a voltage which causes a current to flow, and that's what you're picking up, which in the context that we were talking about creates hum, which is undesirable. On the other end of your radio, when you feed that voltage into your antenna, and it creates a magnetic field, and that field crosses the other wire, which is your receiver's antenna. That's how radios work.
Yeah, you are developing a magnetic wave that is collapsing, and when it collapses, it forms an electric charge, and then it goes back and forth between an electrical wave and a magnetic wave, and that is what gets transmitted through the atmosphere. Well, not just through the atmosphere, you can transmit it into space.
Yeah, yeah. Well, I say what I never really thought about was, on one hand, is how the device that we're all wanting to get this license so we can use. But if you were an audiophile, you'd look at it differently, because that's what's going to cause hum in your hi-fi system.
Yeah, but our radios have a lot of filters in them for the purpose of selecting a frequency, filtering out the other frequencies, amplifying the frequency that we want, whether we're receiving it or transmitting it, and then going on through different stages of amplification and delivering it to either the speaker or earphones so we can hear it, or delivering it to the antenna so we can transmit.
Yep. Another comment talking about the size of your capacitor.
Uh-huh.
I pulled the manual from my Tech Corsair 2 down, and its big capacitor is a 47,000 microfarad capacitor.
Yeah, when we talk about a microfarad, that's 1/1,000,000th of a farad.
Exactly.
A farad is a very large amount of capacitance.
It is.
So even 47,000 microfarads, it's only 47 millionths.
Yeah.
Well, no, that would be 4.7 thousandths of a microfarad. I mean, of a farad. 4.7 thousandths of a farad. Yeah.
Yeah.
Would be 47,000 microfarads. Got to get the zeros all transposed correctly.
Yeah. Well, I found out these little interface boxes I built to hook the radio to the computer has got the Vox circuit, which makes the push to talk work. And I picked up a 47 microfarad capacitor and put it in there to hold the charge on the base of the transistor to make it work.
Right.
It didn't let the radio go back into receive fast enough.
But
So
you know what?
I dropped it down to a 10 microfarad and it worked just fine.
Gentlemen,
But
it is
we're
9
done.
o'clock, so the class is over. If you want to sit around and talk, we can.
If anyone wants to hang around, there is one more demonstration I can do real quick. We talked about field effect transistors. They don't depend on current, they are voltage.
I've got a field effect transistor hooked up here. Come on, make contact. Still don't think I have it right. These alligator clips are a pain to work with. Okay. Can you see the blue LED?
Yeah,
All right. This is the field effect transistor right here at the end of my finger. And it works just on electrical charge, not current. Right now it's conducting because it is charged. If I touch the ground and the lead, see if I can get it to, there we go. Now it's discharged. If I touch the high side and the gate, I turn it back on again. Just the electrons transferring through my skin from the positive to the gate turned it on. And I can drain the gate going to the ground. There's no current to speak of. It's practically not, in fact, just sitting here in the atmosphere, it's picking up enough electrons, it's starting to slowly come back on all by itself. So we're very, very sensitive. Almost, we're talking zero current here. We're just talking a few electrons turning it on, turning it off.
Yeah.
Okay, like Howard said, class is over.
Yeah.
But you
Thank
know, you
you.
can do all kinds of circuits.
Here's one. This is a pulse generator.